Welcome to the Space System lecture of Distributed Cyber-Physical Systems course. You may wonder why at all we are discussing space systems here at this course. The answer is quite simple. I mean, the space systems are those types of systems which are most cyber physical of all of them, basically, because they are remote and distributed by definition. And the physical aspect of their existence is one of the most important aspects of their operation at all. So let me introduce first to the context of space. We will talk about the orbits and the environment that space systems have to cope with. And then I will share with you like the general principles and the ideas behind construction of space systems. And then I will show you in particular, how space systems, cyber-physical systems operating in space are being designed and being tested in order to prepare them to face the physical reality of either close or deep space. And in the end, because it's the most fun part of it, we will discuss the examples of failures and what lessons can be drawn from those failures. Um, and you will see that in most cases that the physical aspect of the system has failed. Um, so let's get to it. Let's start with orbits. What do those things have in common? They are all satellites. Some of satellites that we are having are natural, like the moon. But there's a lot of satellites which are artificially made by humans. And they are either crewed, so there are human beings on board that can operate and do experiments and perform the activities. But most of them are to some extent automated. Uh, some of them they are more automated. Some of them they are operated absolutely manually. Those who are far away usually have to be to some degree autonomous because of the delay, the communication delay between the Earth and the probe. Those who are on low Earth orbit, as you will see, are very close by, and they can be easily operated manually. So yes, we know that the artificial satellites might be useful for us, but how to get there? Um, Main thing is we simply have to launch them, meaning we have to push them so long and with such a force that they achieve the speeds which enable them to travel so fast around the Earth that the Earth, being the sphere or geoid as we call it, because it's not a perfect sphere, simply recedes as the satellite is traveling around it. This is called the first cosmic velocity, and it's about 7.9 kilometers per second for Earth because it depends on the size of the planet. And in fact, this has to happen obviously above the atmosphere, so around at least 100 kilometers above Earth's surface. But actually, then you have still a residual drag. So the practical orbit starts to be at 350 kilometers above Earth's surface and higher. And the whole process of launching the satellite into orbit is surprisingly quick. Just to reach 100 kilometers on SpaceX Falcon 9, it's about two and a half minutes. So it's really fast. Then obviously it will take some time to reach the 7.9 or around kilometers per second of the orbital velocity, the velocity that is required to maintain the orbit. But still, it is matter of minutes or perhaps hours for the very far orbits, and then satellite is there, and since there are no or the drag or the forces that are counteracting the movement of satellites are very weak, and essentially satellites on the high orbits can stay there for decades or hundreds of years easily. As said, we have different orbits, and we can, kind of divide them on different types based, for example, on altitude. There are very low Earth orbits, which are spanning from, as I said, practically speaking, 300 kilometers above Earth's surface to 1,500 or so. So still below Van Allen belts, which are the regions of increased radiation, the radiation trapped, the particles trapped by Earth's magnetosphere. And those are the orbits which are very close, where the delay of the communication is very low. And then we are having higher orbits, which can be like 16,000 kilometers for navigation systems, up to 36,000 kilometers, where is geostationary orbit, which is used for telecommunication purposes. But here already the delay, the latency of the communication. So the time that is required for the electromagnetic wave to propagate to satellite and be processed and get back to the user, it's few well, it's already tens of milliseconds at least. So this can really affect the telecommunication. But that's not full story about the orbits, because also the plane on which the satellite travels matters. Not only the altitude, but what is the inclination of the plane, of the orbital plane, with respect to equator. And there are, let's say, high inclination orbits like the polar one that you see on the animation, which are very useful for mapping the Earth's surface, as you can see, because the plane of the satellite movement is stable, that doesn't change, but obviously beneath the satellite, Earth rotates. This movement of the satellite, or rather Earth below the satellite, is called traversing, and we can expect that over some period of time, the whole Earth could be mapped, or satellite will be visible from every point of Earth at some time. If we decrease the inclination of the orbital plane, we are starting to talk about lower inclinations or equatorial orbits, which can be useful for telecommunication purposes, because then satellite does not see or does not have an access to the whole surface, but instead is visible on over the regions, which is used when you want to use the which is useful when you want to use the satellite as a telecommunication relay. So here are the ground paths of such orbits. The polar orbit example is the yellow one, so you can see satellite visits polar regions on north and south, and then by the moment it gets back to the same, let's say, to the equator, the Earth has moved like 1,600 kilometers. The lower inclinations obviously limit the access to the higher latitudes of the Earth. And then we have an equatorial plane, which is red, so the ground path is only over the equator. If you push out the satellite 36,000 kilometers above Earth, so for the geostationary orbit, then it will rotate around the Earth with the same ratio as the Earth rotates itself. So it will seem to be hanging over just one spot, over the equator, which is extremely useful, as you can imagine, for telecommunication, for simply relaying or broadcasting the information over selected regions. Obviously, there are some tricks. It's not that you can go wherever you like. I mean, because there's always a limit of the power that you have and the fuel that you have. Therefore, there are some tricks for traversing between the orbits. It's called Hoffman maneuvers. And then just by applying simple burns at the perigee and the apogee of the orbit, you can change the orbit, for example, here from the geostationary orbit, the red one. Just one burn in one place causes you to raise the apogee of the satellite, and then you have to burn another time to circularize um, the orbit, for example, on the graveyard orbit, which is 300 kilometers above the geostationary orbit. And you see, like, by the fact that we are having a graveyard orbit, it shows you how important is the fuel and the energy aspect of the satellite operation, because it takes so much energy to get back the satellite from the geostationary orbit to down to Earth, and I mean to splash it into the ocean or burn into the atmosphere, that it's simply not economically possible, not technically feasible. It's much easier to save just a little bit of fuel, to have those two burns to raise the orbit, geostationary orbit, to a geostationary plus 300 kilometers, which is graveyard one, and then satellites stay there, well, until the end of time, basically. So as I said, fuel is the ultimate currency for basically everything that is happening mm, in terms of satellite system operation. It affects mission time. It affects where you are capable of getting off, which orbit or which celestial body. Maneuvering, if you need, it's very limited. I mean, when you are on a given orbit, uh, when when you are on a certain orbital inclination, changing this inclination takes so much power that it's almost impossible to be done. Like, uh, if you are launched into equatorial orbit, low Earth orbit, like 500 kilometers, and you want to change it to a polar one, the energy required to do it is twice the one that is required to just get you to the equatorial orbit. And you are using a huge, powerful rockets, controlled explosions of many tons of fuel to release this energy. And then you are just a small satellite with a small tanks, with a very, very small engines. It's absolutely not possible to change the inclination like that. So we are very, very constrained by the physics. Then fuel is required for station keeping, just to counteract those small disturbances that are affecting the satellite. And it used to be used for controlling the attitude of the satellite, so the angle it is located with respect to some object of interest. But now we have technologies that it can be done electrically by reaction wheels, by magnetotorquers, by stuff like that, or by some more efficient electrical means. So it's not the case for the moment. Therefore, if we want to travel far, we need to be smart. And we know how to save a lot of fuel by using the gravity of other bodies. It's called gravity assist, and it simply means that we want to slingshot ourselves into the from one body to the other celestial body, and then using this gravity pull when you approach the celestial body to really to speed up, then burn at the engines at proper moment or place with respect of the celestial body, and then sling yourself outside of this body somewhere else, most likely the other celestial body. This saves a lot of fuel, but there's a trade-off. It will cost you a time, because the order or the location of the bodies, celestial bodies that you are using for your gravity assist operation, it will change over time. And in general, it will change. You cannot count that it will be as you want, whenever you want. You have to adjust your mission time. You have to adjust the speeds that you have. You have to adjust also the moment where you start, when you start your mission, just to be able to use other physical bodies to help yourself travel around solar system. So this is tricky. It is possible. It makes your life easier on one hand, let's say in the terms of the design of a system, but on the other hand, you have to sacrifice something like time, for example. By now, you should know that satellites and probes have to interact with space environment. They are in the free fall in the vacuum, which gives no drag. So you need to exert force to speed up and also exert force to brake. There's no drag that will slow it down. All the fuel that you are using during mission has to be taken from the beginning of the mission. There are now just two examples of refueling mission happening by Northrop Grumman, and they are refueling and refurbishing basically the geostationary satellite. So this is slowly changing, but we are in a very early phase of this operational technology actually happening on a larger scale. So it's kind of an interesting fact. It will change. We are going there, but we are not there yet. As I said, satellites cannot change orbits very freely. But you can be smart and trade off the energy used versus time for the travel. Um, geostationary satellites, they are very useful, and I mean, being on the geostationary orbit is kind of a special, so it gives you like the capability of a satellite to hover over one place over the ground just by the fact that you are far away and you are rotating with the same angular velocity as the planet. There are some Lagrange or called other way liberation points which enable you to place yourself in locations where the forces from different celestial bodies are canceling out themselves. So when you put yourself in such a liberation equilibrium point, you will move along those bodies, but you don't need any extra power to maintain this position, roughly speaking. And then to travel longer distances but save fuel, gravitational slingshots are required. So that's the overview of the orbital stuff. Now let's look at the satellite and probes. They have different sizes and functions, and they come in different sizes, starting from 60 centimeters ball of Sputnik 1, the first artificial satellite, launched in 57 by Russians, through a few meters of largest size. Cassini orbiter was already 6 meters with nuclear thermoelectric nuclear generators on board. Sometimes for measurement, large bombs are used, like in terms of NuSTAR, 11 meters. Very famous Hubble Space Telescope. It's 13 meters, size of a bus. Then we are having very famous Voyagers, size of a truck. The stations are large because there's a lot of additional equipment required to support life of astronauts or cosmonauts or taikonauts. Skylab or Mir station, they were in ranges of tens of meters. The largest man-made object, International Space Station, is a size of a football field, more than 100 meters in largest dimension. Satellites are usually divided into two parts, payload and bus. Payload is something which gives the reason of a satellite to be there. So, like, it's performing the main mission activities. It can be radio frequency repeaters. It can be communication links. It can be cameras, telescopes for observing the Earth or some astronomical objects. Radars, spectrometers, clocks for navigation. Navigation systems, very important stuff. On the other hand, we are having a bus, which provides everything that is required for payload to work there in the orbit, which is guidance, navigation, control, attitude determination, tracking, telemetry, command and ranging, power generation and power storage, structure, holding everything mechanically, propulsion if there's required to either station keep or change the orbits, and thermal management, passive or active, depending on the design. Typical operation of a satellite system. We are having a satellite, primary satellite here. There must be some station which is commanding and getting sometimes the telemetry data from the satellite. Satellite performs its activity, whether it's getting radio data, whether it's observing, and then it's downloading, downlinking the data to a station that is receiving this payload data, the useful information that has been there and collected. Sometimes it's used with crosslinks to other relay satellites, which then also downlink and provide forward links if required. So basically, there's one or more ground stations. As you can imagine, unless we are talking about geostationary satellites, satellite will orbit the planet. So if you don't want to wait hours for next visit, you have to have more than one ground station, obviously, because satellite will move around. You attached to ground on a ground station will move away, satellite will get back. If there is no ground station around, you will have to wait several revolutions of a satellite to be again visible at the ground station. Deep space probes are a bit different than typical satellites. Cassini spacecraft, great example of a deep space probe. On the left, on the right, typical Earth orbiting satellite. There's one obvious difference here. There's no solar array on a deep space probe, simply because far away from sun, there's not enough power, the sunlight, to be generated into electrical power that can supply the probe. On around Earth, it's pretty decent. It's 1400 watts per square meter. There's a lot of power to be used, really, and obviously closer to sun as well. On the other hand, you can see that the communication dish is large, so it means it has huge gain and it's very direct. There's a high directivity of the antenna, which is required to really being capable of establishing communication link. And also it requires that there are large antennas on the ground, basically. With um, uh, with uh, with Earth orbiting satellites, it's easier. Usually, the large antennas are used only when you want to have a high data rates. As I didn't mention, I think I mentioned it before, but here, if you don't have solar powers, what can the solar power? What can you use? Usually, you have to use nuclear power supply, which is basically taking the heat, the decay heat of a nuclear material, and then it provides heat to a Seebeck converter, which is a thing, which is the opposite of the Peltier one. It's generating the electrical power on the difference of temperatures. So that's why we are having generators here with radiators. So they cool down on one side, they are heated on the other, and the difference causes them to generate electrical power. Very interesting concept. Unfortunately, not used that often nowadays due to ecological concerns. But it's the main enabler for deep space exploration. I mean, beyond Mars, basically. So yes, let's get to harsh environment of space. As you've already heard, there's a lot of sun radiation in terms of visible light and thermal radiation that is being generated by sun. And by the Earth's orbit, it's sufficient really to power everything using solar panels, uh, and also to quite easily maintain the temperature stability around 0 to 10 degrees, just by the fact that that's an average temperature of the Earth. That's gonna be quite similarly average temperature of a satellite. But average is not enough. The particular temperatures of different surfaces of a satellite will be different. The one which are sunlit can be 150 degrees Celsius plus. The one which will be turned into the deep space is going to be minus 100 easily. And obviously, satellite is also being eclipsed. It's either fully in sun and then it's going behind the Earth in the Earth shadow. It's fully eclipsed. So the temperature variation can easily reach 200, 250 degrees, and it will change over 45, 40 minutes, because only at least on low Earth orbits, because we are talking about 90 or 100 minutes of the orbital period here. The temperature, the reference temperature, as you can see, falls down very quickly. I mean, the reference temperature, so like the average temperature of a reference sphere that is placed on a given orbit with respect to the distance of the sun. So, as I said, around Earth is 0 to 10 degrees. Around Mars is already minus 40. Around Jupiter is already minus 150 easy. Saturn minus 180. And we are getting asymptotically to absolute zero, far away from the sun. Mm, so it's cold. Electronics doesn't work very well in such cold environments. Simply, semiconductors stop working, and they do not keep the parameters. So this has to be taken into account when designing the the probes. On the other hand, when you are visiting Mercury, so first planet from the Sun, the temperature can easily reference. So the average temperature can easily reach 180, which is over. It's like easily 30 degrees over what is the maximum range of all the military electronics that we are having on Earth. So also very hard to build a probe that is capable of operating there without very sophisticated isolation and active thermal control. In space, there's no air. There's a vacuum, and it's a quite deep vacuum. It will affect the heat transfer heavily. So you can imagine that all the equipment that you put there into space, it's enclosed into a vacuum bottle. There's no heat transfer, only just by the radiation, infrared radiation, and conduction. If you connect metal pieces of metal that will conduct the heat, you will have the conduction transfer, but no convection, which is like raising of the hot gases from above hot element, which is the most effective way of exchanging the heat. That's why we are using radiators on ground. It doesn't work in space. So you have to design and test electronics accordingly with thermal frames, heat pipes. It will also affect the behavior of mechanical devices. If you stick two pieces of metal, it can cold weld together, and then it will obviously affect the mechanisms. If the elements which were supposed to be separate are no longer separate, it will not operate. Also, the vacuum poses some challenges on how to build the components and the printed circuit boards, because all the voids that will be there can crack open because of the gases stored inside. Also, outgassing is not something that you want to desire, especially if you have spectrometers on board. You don't want to have additional gases, being released there. You want everything to be really in vacuum because you want to measure something down there on Earth or down there on the planet Mars. You don't want to measure something that has outgassed from your equipment. Atomic oxygen, which is a case for low Earth orbit, is very aggressive one. It will start reacting with almost all the materials which are there. And yes, on low Earth orbit, also residual atmosphere drag can be some issue. It will reduce the lifetime. If you want to use a very low Earth orbit, so like 350 kilometers, which might be very beneficial because you are close to to Earth's surface. If you want to take a picture, it's easier to make it from being close than being far away. And also the latency, the communication latency is quite low. But then the residual drag will affect the mission lifetime. It will, if you do not counteract with the engines, you can deorbit within weeks, basically. There's also other aspect of the sun. It's the ionizing radiation. As you perhaps know, sun is the nuclear reactor. It's the constantly happening nuclear explosion, which is counteracted by the huge mass, the gravity contraction of the sun. So there's radiation. There are particles, ions, protons, electrons, and they all form solar wind, which is escaping sun along the field, the lines of magnetic field. But Earth is also magnetic. I mean, the magnetic field, there's a connection between sun's magnetic field and Earth's magnetic field. So there's a highway through which the solar sun can travel this quite large distance between sun and Earth and hit the Earth's magnetosphere, forming the Van Allen belts. So the areas of high radiation, because there are particles which has been released from the sun and are trapped in this magnetosphere, and they are moving around. They are there, and they are of concern for constructing satellites, because if satellites are not prepared, or probes are not prepared for withstanding such radiation levels, they can simply fail. But on the other hand, we have a beautiful aurora australis and borealis thanks to that, because the same radiation is ionizing the upper parts of the atmosphere, um, showing the northern lights, a beautiful spectacle. So, as I said, solar wind, it is mainly protons, some alpha particles as well, so helium ions. There are traces of heavy ions and a lot of electrons. Its speed is like mean speed is 450 kilometers, but it can reach 800 kilometers per second. And yes, you can see on the right the animation of coronal mass ejection, which is like the mm, very very abrupt events happening on the sun, where a lot of sun's corona is being ejected into the space. You can see what is the size of this protuberance compared to Earth. So it's like 10 times size of Earth itself. They have huge velocity, over 2 times what is the maximum for solar wind. Very high particle density. It can cause satellites to switch off. It can cause electrical grids to switch off, because such amount of charged particles attacking the magnetosphere cause the Earth's magnetic lines really to being pushed inside the Earth. So there's like the magnetic vibration of the magnetic field of the Earth. And this can induce very large currents into the power grids, and then burn the equipment, burn the transformers, and so on. They can last for a few days. We can, when we are trying to predict them and prepare, meaning switching off the potentially affected infrastructure, just to save ourselves some troubles. This is something which is called space weather prediction. So sun's activity in general, like there's this level of solar wind which is constantly being released from the sun, but the number of the coronal mass ejections or flares, so like the bright flashes of radiation from the sun's surface, they differ. I mean, the number of occurrences over the unit time, they change over time. and they come in cycles. And we have solar cycles. They are more or less 11 years. The period of solar cycle is 11 years, um, 11 years long. And as you can see here on the pictures, we are having the sun's minima and maxima for past 10,000 years. So as you can see, there are cycles which are higher, lower. They can for millennia almost. It can go down, quite low activity, and then it can raise up again. So we are in quite active period with a large number of sunspots, and this is like past what is it? It's 140 years. We have a smaller cycle, this 11 year cycles. Um, right now it's quite quiet period, but in general, compared to what we see in history, in ice, for example, or in trees, it's quite active. As I mentioned, there are Van Allen belts, so the regions of radiation which is trapped in Earth's magnetosphere. And basically, there are two Van Allen belts. One is spanning from 1,000 to 12,000 kilometers. It is the proton one. But over the so-called South Atlantic anomaly, it's just 200 kilometers. And it consists of high energy particles, electrons, and protons. And there's outer one consisting mainly of electrons, and it spans 60,000 up to 60,000 kilometers, so twice the geostationary orbit, basically. And the density of radiation, trapped radiation, changes over time, changes with the sun activity, but sometimes subject to very strong coronal mass ejections. There could be another one created, the transient Van Allen belt, which can affect satellites on, well, depending on where it shows up. It used to show up in the region of geostationary satellites, so like 36,000 kilometers. So this is very dangerous for our telecommunication infrastructure. This has to be taken into account that we are actually discovering these things happening as we start to explore and utilize space for practical purposes, because this has been discovered like 8 years ago. We have another source of ionizing radiation. Those are cosmic rays. And they are coming from the galactic center or some extragalactic sources that we are not even sure what they are. We just measured that they are emitting particles, the ionized particles with huge energies. Well, there's a lot of them coming in very similar manner like sun-like protons, so they are perhaps coming from other stars. Let's say the highest energy ever recorded of such particle was 51 joules, which is the energy of one single particle, ionized particle, to be equivalent of baseball, which is like 150 grams almost, at the speed of 94 kilometers per hour. That's a huge energy, This is a particle that can cause a mechanical damage almost to a let's say semiconductor structure. Mm, yeah, so this is something which has to be taken also into account. So we have a sun, different sources of sun radiation, and we have a cosmic radiation that is coming from extra solar system sources. Radiation is not the issues with the electronics affected by radiations are not caused only by sun and some extra solar sources, but also other sources of radiation, which can be impurities of integrated circuit packages, rock formations, or earth crust. There are some regions of Earth where the radiation background is simply higher because of some residual isotopes which are radiating, which are not stable in the rocks, in the ground, and this can also cause the issues with electronic bit flips, upsets. Also, human activity can cause radiation effects that will affect, in general, electronic systems. So nuclear power stations, with nuclear warheads, if we are into the war stuff, high energy physics, the accelerators, the medicine, the proton beams used for cancer treatment, and so on. And there are also atmospheric neutrons, so the rains, cascades of particles caused by galactic cosmic rays, which hit the atmosphere and then caused the secondary effects, secondary crashes, ionized some particles from the atmosphere, and they can affect uh, electronic circuits on the sea level, basically. So I think that this is it for environment. Uh, I think this is a good beginning. So now you know that the equipment, basically electronic, but also mechanical systems, are affected in very, very strange ways sometimes um, by by the environment, by its radiative aspects, by large temperature changes, by vacuum. So it's something that is a large challenge for the creators of the space systems. But this is let's say normal environment that those systems have to cope with, and this can be done. So about what exactly bad is happening to semiconductor devices, to electronics, we will discuss in the second part.